name is Justin Phillips, and I am presenting on activity 4, which was determining the effect of free fatty acid content on biodiesel production. And my group member was Alpo. The presentation will be as follows: well, the objectives, the background, the environmental health and safety synopsis, and experimental design, results, data, discussion of results, conclusions, recommendations, show you my references. Like the presentation states, we're determining the effect of free fatty acid on biodiesel production, and we record our results quantitatively and pictorially. And the reaction takes place is transesterification, which is the conversion of triglycerides into biodiesel, and it's given by the reaction shown. A triglyceride with 3 moles of methanol using a catalyst will yield fatty esters and glycerol. Some background on biodiesel: it's been used as early as the 20th century when diesel was first used. Rudolph Diesel used peanut oil in his example, and it's alternative to using just straight vegetable oil and to petroleum-based gasoline. It is a renewable source of energy, non-toxic, biodegradable. However, when there are impurities present and you're trying to produce it, soap is produced. In this experiment, we use methanol and pelletized sodium hydroxide, and both of those are skin, eye, inhalation, and ingestion hazards. So for personal protective equipment, we use splash-proof goggles, nitrile gloves, and work under the feet. So the experiment designs as follows: we use soybean oil as a source of triglycerides. Use twice as silicon methanol to ensure the reaction goes to completion. The homogeneous catalyst, just means it can be dissolved in a medium, was the sodium hydroxide, and we use 1%. And to see the effect of the free fatty acid content, we use varying amounts of tall oil from 0.25, well, from 0 to 0.2 to 2%. And the reaction was kept at 65 degrees Celsius, ran for at least an hour, and 350 revolutions per minute. And this is a picture of our experiment. We have a beaker on a hot plate covered with paraffin and indicate the time and percentage of tall oil. And these are the numbers of the reactants we use. We use 50 grams of soybean oil, 11 grams of methanol, and 0.5 grams of the sodium hydroxide, which we crushed. And here are the results. As you can see, in 0%, there is no soap. And this one was a little weird because we didn't see soap in the higher separations. So that was our trial A. And trial B, there's 0% total, and even at 0.25%, there was soap being made, all the way up to the 2%. Here's the data. And trial A was kind of funny. Trial B was better. I'll discuss why. For the glycerol, there's over 100% yield, but that's due to the excess of methanol. And the percent yield was nearly the same for biodiesel, but there was less biodiesel with higher percentage methanol. And in the earlier experiments, where there was a lot of soap, it was hard to separate the layers. The soap was present. And in the end, biodiesel produced, however, soap was produced when tall oil was introduced, even at low percentages. So I would recommend to reduce impurities if you want to make biodiesel. And use clean glassware, because that's where error was introduced. When separating, we weren't cleaning all the time, but the second time we did. Allow ample time to separate layers. And further research into biodiesel production on a small scale could be done in this class. We could try different separation methods, more trials of course, and possibly use a different catalyst for this.
Can you go back to your data? How did you calculate the % yield of biodiesel?
We did the theoretical yield and information, but actually the theoretical was like 100.
So your batch sizes were different sizes?
No, they weren't.
And they all reacted the same period of time?
No, some were left on longer because we were doing a whole bunch of them at one time, so some were left on longer.
I would say that indicating how long they were on there would be important. Because, for example, if you systematically took off the 0 one first, and then the 0.25 one, and then the 0.5 one, and then the 1, and then the 1.5, and then the 2, if you systematically went in that order, then you would expect to see different amounts of yield, and it would make sense why your yield would be going up.
Yeah, it wasn't, we weren't in that order. We were out of order.
What's the way that you could do it so that you could do a lot at once and still have them all have the same time?
More glassware. We had only one funnel for one thing.
So how else could you do it?
Take it off at a certain time.
Yeah, I would say take it off and quench the reaction. Because if the reaction is, if you have it going hot, it's going to go a lot faster. So if you chill it, it'll go a whole lot slower. For example, when in the laboratory, when they use the little stainless steel reactors, they actually seal those things up. They look, you just screw the lids on, and you throw those in an oven, and you run those guys at like 180 C. So they're really hot. So they're cooking really fast, which means that when you take those off, don't do this with Pyrex, but when you take those out of the oven, you dump them into cold water, because that slows the reaction down dramatically. It won't necessarily end it, but it'll at least slow it down dramatically. And I would suggest that your data would be more consistent if they had all gone at the same, for the same period of time.
Yeah, they did.
Any other questions? I think she needs at least one more before she can sit down.
Do you have a method for separating soap and oil from each other, or is it?
No, they were all just.
Okay.
Why does it make soap?